So LISA is a mission that will involve 3 drag-free spacecraft using the same kind of drag-free techniques as were developed for Gravity Probe B, so it relies on Gravity Probe B technology in that sense and building on Gravity Probe B technology. These 3 spacecraft at the corners of a triangle, 6 million kilometer arms separating them, and looking for waves of warped space and time. And so it's the 3 aspects of space-time warpage: warping of space, warping of time, and dragging of space, but in a wave-like form propagating through the universe, produced by different distant objects. LISA will see primarily the effects of the warping of space. It's a stretching and squeezing of space, causing these spacecraft to move back and forth relative to each other as these waves go by. One of the objects that we will study with LISA is a big black hole with smaller object, a smaller black hole or a white dwarf or neutron star going around the big black hole. As the big black hole spins on its axis, and if the smaller object is in an inclined orbit, as shown in the next in my graphic, that drags the orbit into a turning motion. And so you see the little black hole going around the big black hole in its circular orbit. Each time it goes around the big black hole, you get an oscillation of a stretching and squeezing of space, of stretch and squeeze that's shown down at the bottom. So you see something going up and down in oscillatory fashion. Each of those little wavelets going up and down, or each up and down it comes from the small black hole going around the big black hole. But then the dragging of space into motion by the big black hole causes a precession of the orbit. The orbit turns as shown by the red arrow, and that causes a modulation of the waves. And so you see this modulation. And so we, with LISA, will get very high precision measurements through the modulation. We'll see very high precision measurements of the dragging of space, dragging that orbit. So if you come back to me, you'll see the orbit plane go around and around through those modulations, but only by virtue of Gravity Probe B's having verified the relationship of spin angular momentum to the dragging of space, and told us, yes, general relativity was correct about that proportionality constant, and it corrected it as the angular momentum that's doing this. And so we have a firm foundation for now interpreting these observations. With Gravity Probe B having done the calibration in that sense, with LISA then, when LISA flies, we will be able then to interpret the observations. When we see the modulation of these waves, we'll be able to interpret those observations and say, there was a black hole. It was spinning at a certain spin rate, which we can infer from the observations, and we can infer it with complete confidence because Gravity Probe B has shown us the relationship between spin angular momentum on one hand and the dragging of space on the other hand.